This is the final presentation of Team 12's submission for Project 3, affectionately titled the Rho Rho Robot. L3 Harris Technologies has asked that a prototype robot be built to model a Mars rover that can be used to autonomously deliver supplies to a Martian base. The rover must follow a predetermined pathing and know precisely where it is to deliver the supplies to. In addition to delivering cargo, the robot must be able to navigate hazards on the Martian surface like uneven terrain, debris on the track, and obstacles that must be avoided. All of this must also be accomplished within a set time frame, set to model the possible sensitivity of the cargo to the harsh Martian climate. To create a scale model of the robot, the team was provided with a Raspberry Pi and Lego bricks and Mindstorm components to induce motion.
This section is about the project management, where we'll discuss the diagram we created at the beginning of the project to lay out our ideas and discuss the strategies we used. This is the functional block diagram. Here we have laid out 4 major systems for the robot: the navigation system, hazard detection system, movement system, and the payload transportation. The navigation system takes a color input to determine if it's detecting a white tile or a black line. The hazard detection takes an ultrasonic input to examine potential obstacles in front of the robot. Together, these systems feed into the movement system, which takes an energy input to spin the motors and move the robot to the target destination. At this point, the payload transportation system drops off the cargo. This is the work breakdown structure. In this diagram, we used the major systems of 4 as the level 1 goals and broke them into the necessary components to make them work. These components consist of building the framework, attaching the sensors, and writing the code. This is the Gantt chart. Here we gave a loose projection of the time management for our design process. According to the chart, we would spend a week brainstorming, another 2 weeks building the robot, and the rest of the time is spent testing and improving the design. These are the strategies we use in our meetings. Most meetings would focus around 1 to 2 aspects of the design. These focus points were decided at the beginning of each meeting after a short discussion on what parts of the robot are struggling the most. After deciding what we're doing, we assign one person to the coding while the other 2 focus on building. The meetings would last about 2 hours each, allowing plenty of time to improve the design.
When it came to designing the physical features of the robot, we first identified each of the technical requirements our robot should satisfy and thought how we could make it so our robot was worse at completing these tasks. This worst possible method provided some key criteria for us to satisfy when designing our robot. The robot should only accept human input to begin its journey. It should have several input methods to detect both the path it was to follow and any hazards in its way that it could either avoid or surmount. And the robot should be stable so as to support the weight of both itself and the cargo without collapsing or having the motion suffer. With these criteria in place, we drew inspiration from other Mars rovers like NASA's Curiosity. In particular, we wanted to emulate the adaptable suspension that allows Curiosity to navigate over uneven terrain. With this in mind, we began building the first iterations of the prototype. Our first design focused mostly on stability and speed as we familiarized ourselves with the components provided to us. Then, as we encountered issues, we took apart and rebuilt our robot to remedy the problems that affected each individual iteration of our robot, still focusing on stability and efficiency. The first few designs saw several remodelings as we tried to find what worked and what didn't. Stability and power efficiency remained at the forefront of our minds throughout the first 3 iterations of our prototype. Design 4 was where the prototype began to emerge, and as such, it was our penultimate prototype. Realizing that the motors added considerable strain to our frame, we reinforced the lower part of our robot to withstand the stress imparted by the motors, the Raspberry Pi cage, and the eventual cargo. Part of the reason Design 3 was abandoned came from its cargo area. Design 3 lacked an autonomous cargo drop-off method, so a motor previously allocated to steering was used to operate an arm that would open and close to hold cargo in place. Now, with only a single motor to steer, we needed to redesign how our robot would navigate curved portions of its path. In the first image, you can see an axle holding the front wheels attached to a motor that would rotate given certain inputs from line finders and ultrasonic sensors. The cargo bay also took on a triangular shape to simplify drop-off, and a second set of wheels were attached to the front axle to even out weight distribution. Our fifth and final design saw every question posed at the beginning answered with a yes. The somewhat unbounded steering system allowed the robot's front axle to move vertically, meaning it could traverse small changes in elevation. Line finders, ultrasonic sensors, and an inertial measurement system, or IMU, were added to provide the necessary inputs for the Raspberry Pi to function autonomously. A larger claw was added to secure the different cargo to the robot, and turning was made easier by removing the tires from the front wheels, thus decreasing friction with the ground. Seeing the progression from a small, quaint design to a robust cargo-carrying vehicle, the advantages this iteration has over others is present in three main areas: the stability, motion, and carrying capacity. While the robot has a slight dip, this means that the back wheels do less work to push the robot compared to if they had to pull the weight of the vehicle instead. This also means that on straight or downhill sections of the path, the robot can travel very quickly as the robot falls forward in a way. When the robot is behaving like this, it is capable of a top speed of around 37.5 centimeters per second. Such a speed means that the robot easily satisfies the time restriction on delivering cargo. The turning system, when suspended correctly, makes turns up to 90 degrees possible. And our final cargo system had 3 separate points of rotation, allowing the claw to grab nearly any shape provided. Solids would rest against the claw and the sloped bed, so that when the claw opened, the cargo would fall neatly down to the drop-off point.
Right, so now we're going to talk about the design philosophy for the software. So to start, it was mostly just trial and error. It was a lot of just thinking of an idea, putting it into code, and then running the code, seeing if the robot would actually work, if that code did what we wanted it to do. So by the time we were coding, the robot design was already finalized. And so we knew the code had to work around the specifications that we already built. So there wasn't much in the robot that we could change. If we couldn't get something working, there was only small edits we could do on the actual robot itself. So that did limit us a lot, made us have to get creative in our coding. And then the goal was to design easily editable systems. So that meant if something wasn't working how we wanted, we could just, change a couple numbers, maybe switch around a for loop or something, and to try to get it working how we wanted. That was the goal, to make it easy to edit so that we knew during the test, if it didn't work how we wanted, we could just change a couple of things and it had a higher chance of working. So there are 4 main things. The first one is the line finding. So we had 2 line finders out in front on our steering system. Basically, they would both be detecting white. That meant the robot would be going forward. If one of them started detecting black, it would turn the turning mechanism that way and continue going forward, so it would hopefully follow the line. So the turning was based off of just a power. So we had a motor set up to an axle, and the motor would just spin when a line was detected. There's turning the wheels, kind of like how a regular car works. And so we were able to vary the power to make it turn faster or slower. We ended up settling on something that we knew worked best, but it was easy to change. So right here we have the flow chart, basically just as I described. If a black surface is detected, it sets the back axle motor power lower, just so it's going slower, so it's not just going to pass over the line without turning. Turns the turning motor on, and then it waits to keep detecting. Next, it's an ultrasonic sensor. So we actually ended up not needing this, but it was already implemented into our robot before we realized that. So we just had the code in there anyway. Works very similar to the line finding. Basically, if an obstacle is detected, I think we set it within 15 centimeters, then it would just turn on the turning mechanism, keep going forward, hopefully turn around it. So we didn't end up needing it. It was still in our code. You can see the flow chart basically as I described. If it's detected, back axle motor power set lower, so it's not just going to run into the object and then starts turning. Next, we have the magnetic detection cargo drop-off. This flowchart looks crazy. It's actually not that bad. So what we did, we had the IMU just on the side, and basically if it picked up magnetic field, then it would increase a counter by 1, and then our robot would do certain actions based on the count of that counter. And so we ended up hard coding this because we couldn't think of another solution, and we just thought that would be easiest. So as you can see, the count starts at 1. If something's detected, it increases the count by 1. And then all of these little boxes were if statements in our code. So if the code equals 2, 6, or 11, it does a certain thing. So you can see here, set back axle to slightly less than regular, and then start turning to the right. So that would be in all the branching pathways in the track, that would be there. So it would know once it hit that magnet, it would start to turn to the right. And then the rest of the counts just go through. They just do different things like lift up the cargo arm or just make sure that the robot doesn't actually turn itself. And then the speed test, let me move this. Speed test was super easy. So we just did tests to determine the relationship between speed that it's actually going and the motor power. And ours actually came out to be a linear relationship. So we knew that the speed times 8 divided by 3 would equal the motor power we needed. And so our code was literally just, we put in the speed we want, it multiplies that number by 8/3, and then tells the motor to go that fast. Now let's talk about some positives and negatives of our prototype system. So first positive was that the build was very stable. So you could pick it up by the pie holder, it wouldn't fall apart. You could set it down pretty hard and it still wouldn't fall apart for the most part. And so it was pretty hard to break. And then the large frame allowed for lots of modifications. I have a picture of that here. You can kind of see the frame. It's built out of those pieces with all the holes in them. And then we had the same thing down there. So it kind of had 2 levels. So in those holes, we could attach really anything we wanted. So that made it pretty easy to build, pretty easy to modify if something wasn't working. We were able to do the speed test pretty easily. That was pretty painless. And then we actually spaced out our motors. And so one motor was for the power in the back, one was for steering, and one was for the cargo arm. We really liked that because we were able to space out the motors. So we didn't have like 2 motors doing one thing. That way, not a whole bunch of resources were spent doing just one thing. We kind of liked that. And then the line finding code worked accurately within 0.5 seconds. It's probably less than that. We just weren't able to ever get an accurate time. So we just said 0.5, but it was pretty instantaneous picking up a line. And that worked pretty well. And now to the negatives, a lot to do with the cargo. But first off, the turning system doesn't allow for turns greater than 90 degrees. So one of the things we ran into was that it would detect the line and would start turning. And then eventually the turning axle would get to 90 degrees. And so the wheels at the front would be perpendicular to the back. So the robot would just stop. So then it was unable to move. That kind of hindered a lot of our progress. The cargo holding arm couldn't really hold any of the larger cargo. You have a picture of that there. It's just, it wasn't big enough, wasn't designed well enough to actually hold the cargo. So we were able to hold the one that looks like an ice cream cone, just put that in there, but any of the other ones, they were too big and they didn't fit. The magnetic detection and all the code relating to that, we were never actually able to test it. So we never knew if it worked, and it didn't work during the demonstration. So that's a negative. We kind of need that to be working. And then we had a little battery holder on the side just to hold the battery. And after extended periods of time holding that battery, 10 to 15 minutes, that tended to break. So that actually did break during our demonstration. But as I mentioned before, the robot was well designed, so it's still able to withhold the force of the battery. We just put it on top of the pie, and the robot still worked great.
And finally, this section will talk about our conclusion and the areas of improvement. For our conclusion, we found that while all the necessary systems were in place, many of them would be either inconsistent or limited in some way. The best example of this is with our turning system, which failed because it was unable to turn the needed amount in order to actually move the robot. For the areas of improvement, I have 4 sections listed. The first one is with the line finder. The line finder code couldn't allow for turns greater than or equal to 90 degrees. This was caused by the motor turning too fast, thus making the front axle perpendicular to the back axle. A possible way to fix this would be to physically restrict the turning axle, making it unable to turn to 90 degrees. The second one is the payload transport. The arm of the final design can't reliably hold the payload for transport. This is likely caused by the arm not having the right size or flexibility to carry the payload to the drop-off point. The end being able to move may also have affected the system's ability to hold the payload in place. A possible way to fix this would be to play around with the dimensions of the arm and the platform the payload is being pressed against. That way, the payload can be transported more efficiently and consistently. The third area of improvement is the magnetic detection system. The system built in the final design can't reliably pick up a magnetic field. So it's likely because the IMU sensor, which we were using for a magnet sensor, was awkwardly placed on the side of the final design. A possible way to fix this would be to move the sensor to the middle design so that it can pick up magnetic fields easier. And the last one is the battery holder. The battery holder couldn't hold tons of weight for extended periods of time without breaking and falling apart. This was likely because the holder could not hold itself together very well due to the choices of pieces being used, because a lot of them were very small and unable to take up large amounts of weight for long periods of time. A possible way to fix this would be to build the battery holder with larger pieces to give it a bit more stability.